So hello, in this video, I'll briefly explain what I did in the M4 final hackathon. The goal of this project is to predict whether a person has diabetes or prediabetes using health-related survey data. The target variable is called diabetes binary, where 0 means no diabetes and 1 means diabetes or prediabetes. Because this dataset is imbalanced, meaning there are more non-diabetic cases than diabetic ones, accuracy is not a good metric. So I mainly focus on improving the F1 score since it balances precision and recall and is more suitable for healthcare risk prediction. First, after loading the data, training and testing data, I did some basic data checking. I looked at the data types, missing values, and overall structure. This helped me confirm that the dataset was clean and ready for the modeling. Then I performed some simple exploratory data analysis. I plotted the distribution of the target and target variable to confirm the imbalance. And I also checked correlations between features and the target to see which variables might be important. And you can see from this chart, they say like general health, high BP, and like different work or BMI are more important. And also from correlations results and the visual comparisons, variables like BMI, age, high blood pressure, and general health seemed more related to the diabetes risk. After that, I moved to the feature engineering. Instead of only using the raw features, I created several new variables to better capture health patterns. And you can see from here, for example, I created a risk score which sums up several medical conditions like high blood pressure, high cholesterol, stroke history, and heart disease. The idea is that having multiple conditions together increases overall risk. I also create a healthy score, combining lifestyle behaviors like exercise, fruit and vegetables consumption, smoking, and alcohol use. This gives the model a clearer signal about overall lifestyle quality. In addition, I created BMI category indicators like overweight and obese because tree-based models often learn better from meaningful medical thresholds. I also added variables like chronic burden to summarize the total number of chronic diseases. All of these engineered features aims to give the model stronger, more interpretable signals. Since the dataset is imbalanced, I applied several techniques to handle that. Like for the boosting, you can see from here for the data modeling. So for the boosting models like LightGBM and XGBoost, I used scale post weight. And for random forest, I used class weight. I also experimented with mode to oversample the minority class to evaluate them properly. I use a tenfold stratified cross-validation. This ensures each fold keeps the same class distribution. I also generated some out-of-fold predictions. This means each training sample gets predicted by a model that did not see it during training. This helps prevent data leakage and gives a more realistic estimate of performance. Instead of use only one model, you can see from here, I do some model comparison and also ensemble. I combined the predicted probabilities from LightGBM, XGBoost, and random forest, use weighted averaging. The idea is that different models capture different patterns, so combining them usually improves the stability and generalization. Finally, I tuned the classification threshold. Instead of using the fault of the 0.5, I'm going to find the best threshold here and also use this one. Like I searched for the best one and gave the best F1 score on the validation prediction. This is especially important for imbalanced data because adjusting the threshold can significantly improve recall. After selecting the best threshold, I retrained the models on the full training data, generated predictions for the test data, applied the ensemble weights, and produced the final submission file. That's all for my modeling workflow. Thank you.